And the last workshop contributed papers we have today are from 4 students. We have Thomas Fork from UC Berkeley, who's joining virtually. We have Edward Zhu also from UC Berkeley, both from Francesco Borelli's lab. We have Feng from Rutgers University joining in person. And we have Elizabeth from Auburn University also joining in person. I hand over now to Thomas, who will now show us his work, hopefully. So Thomas, I made you host.
Can you hear me?
We can hear you loud and clearly. And if you share your screen, I tell you that we can see it. Yes, looks good.
Great.
The stage is yours.
Awesome. My name is Thomas Fork. I'm part of the Berkeley group at UC Berkeley, and today I'll be presenting our work on overtaking maneuvers on a non-planar surface. And this work is really motivated by one key observation, which is that much of autonomy and vehicle control is enabled by models of these vehicles. But the vehicles that we use for controlling, the models we use for controlling vehicles are limited to flat surfaces, when many of the surfaces that vehicles drive on are not flat, such as the racetracks shown on the right here. And so my work as a PhD student has been to work on generalizing control-oriented vehicle models to surfaces that aren't flat. And what can we do with these models? Here are some examples of work we've done on computing race lines with different non-planar vehicle models, on computing overtaking maneuvers, which is the subject of today's talk. But we can go beyond the racetrack too. And this is an example of a parking maneuver on a hill done with full obstacle avoidance in 3D. And these are all enabled by non-planar vehicle models, which I'll discuss first, and then I'll lead into the overtaking application later in this talk. Now, before I introduce our modeling approach, we'll make one key observation, which is that if we observe vehicles racing on non-planar surfaces, in many environments, we can treat them as being tangent to this surface. And we can use this simplification for control-oriented models, really to simplify the models so that they're tractable for practical numerical control. And there's 3 main steps that we use for our modeling approach. The first we do is we model the road surface with a parametric surface. And this is really a mathematical tool that allows us to describe the surface and has some advantages that I'll make clear in a moment. The second step we do is to take a rigid body and enforce that it is tangent to and in contact with this parametric surface. And finally, we apply a rigid body vehicle model to this, such as an existing kinematic or dynamic vehicle model or a 2-track model. And there's 3 main features of this modeling approach. The first is that the pose of the vehicle can now be described by the surface parameterization. So on the right here, variables S, Y, and N can describe where the center of mass of the vehicle is, and its orientation can be described as theta S. And this avoids needing 3D rotation groups, even in non-planar geometry. And we can use these coordinates to define lane information or other useful features on a non-planar racetrack. But despite this generalization, we can still keep vehicle velocity expressed in the body frame. And so we can maintain the same form that existing model-based control models use. And so we can generalize those methods, the methods that use these models as well. And we'll see some applications of this in a moment. But obviously, this model now depends on the surface. This is an inevitable fact of this generalization, and I'll talk more about this next. There's 3 main ingredients to this modeling approach. The first that we use is a surface class, which is really a function class for how we'll describe a non-planar surface. Shown here is an elevation map, but we can fill this in for a traditional Fernet frame or non-planar versions of the Fernet frame other more exotic non-planar surfaces that one might drive on. Second, we have our tangent contact assumption, which is primarily an assumption on how the vehicle moves on the surface. And finally, we have a vehicle model, which can be a kinematic bicycle model, a dynamic bicycle model, or a two-track model, or other vehicle models that people use. And we combine these three to get a vehicle model on the surface class. And this high-level pipeline is no different than many existing models that use the Fernet frame or a Euclidean frame of reference, but we filled in these steps for the general case of a non-planar parametric surface. And from this point, the last step to obtaining a model for model-based control is to take an instance of a particular surface class and fill in the general vehicle model to obtain a vehicle model on the surface, which we can then use for model-based control, which we'll do next. In this talk, we'll primarily use two vehicle models, the first being a kinematic bicycle, which is a standard kinematic motion, and we'll impose limits on the net normal force on the vehicle and impose a friction cone constraint on acceleration. And the second we'll use is a dynamic two-track model, which models all four tires individually, which gives it some advantage in terms of torque vectoring and being able to consider the normal force of each tire individually instead of the net vehicle as a whole, and has an implicit friction cone from a combined slip Pacheco model. Now in the figure in the center here, when we compare both of these models and a dynamic bicycle on a flat surface, they're all functionally equivalent in terms of the shape of the race line that they result in. But on the right, when we try out different models on a non-planar surface, the two-track model has a clear ability to better exploit non-planar geometry as a result of the detail of the vehicle that it considers. Now, the first application we can do with these models is to compute race lines. And what we set up was a standard race line problem, practically identical to ones used for planar race lines, where we discretize the track in space, use a co-location method to enforce a vehicle model, impose constraints, and minimize lap time. But what we do differently is use a non-planar vehicle model. And already with this minor change to the problem, we see that the result of the problem is substantially different, especially with the two-track model. Not only do we exploit non-planar geometry, but the vehicle race line on its own exhibits countersteer, drifting, and other maneuvers that are emergent from the optimization problem. And we built off of this observation for computing overtaking maneuvers, where our goal was to demonstrate that advanced vehicle models can enable overtaking, in particular, enabling overtaking when not otherwise possible. For instance, when an ego vehicle starts behind a target vehicle, if both vehicles are identical and the ego vehicle is not directly next to the target vehicle, all the target vehicle has to do is follow its optimal race line, and it leaves little opportunity for the ego vehicle to pass it. But we can build off of our previous observation and try and have the ego vehicle compute a faster, yet still collision-free race line that exploits non-planar geometry using a non-planar vehicle model. So we set up this problem building off of the race line problem. And first, as expected, when both vehicles use the same model, they're not able to the ego vehicle is unable to overtake. But then if we equip the ego vehicle with a model that's better able to leverage non-planar geometry, it is able to find overtaking maneuvers that are viable and could win the race on the last lap in this case. And a few details of this particular maneuver, the ego vehicle starts behind the target vehicle, but when the target vehicle has to slow down for the turn, the ego vehicle is able to pass and is then able to complete the turn using the non-planar geometry and pull out of the turn ahead of the target vehicle. We did this for a second evaluation environment, which was a banked chicane, where again, we're attempting to pass a simpler vehicle model using a two-track vehicle model for planning. And again, are able to pass the simpler model right at the end of the chicane. And again, we see similar results where this is accomplished by cutting the current corners in a way that exploits the non-planar shape of these racetracks. And that's the conclusion of my talk. In summary and in conclusion, we have control-oriented models that can be used on non-planar surfaces. And among other things, these models can enable overtaking when not possible otherwise. And in the future, we plan on applying these models to real-time control and physical hardware experiments. Thank you.
Thank you very much, Thomas. We're moving on directly to your colleague. I open your presentation and share the screen. Yeah, Edward, cool. Yeah, you go. Do I use the mouse to advance the slide? All right. Hi, everyone. My name is Edward Zhu. So I'm with the Model Predictive Control Laboratory at UC Berkeley. And today I'm here to present to you some work that I did jointly with Finn Bush and Jake Johnson on a Gaussian process model for opponent prediction and autonomous racing. So, I'm not going to go over this in too much detail because you all know, but this racing problem, right, can be seen as a multi-agent problem where you have this competitive and adversarial behavior between the agents. And additionally, we have like the safety critical constraints, or we have these critical constraints that we have to satisfy for safety. In addition, we also have that the behavior is typically going to be highly dynamic. However, for the purpose of this work, the key points that we wanted to highlight here are the fact that there is no voluntary sharing of information. This means that from the ego vehicle's perspective, right, we don't really know the dynamics model of the target vehicle. We don't know its racing policy, which means that ultimately we don't have access to its future plans. Two assumptions that I'm making in this work, and please indulge me because I know the second one is probably especially incorrect, especially from after all of the talks we've seen today. But the first is that we have state traces available from past races. So this is historical data from your opponents. And the second one is that your opponent's state can be measured accurately. So I know that we've talked a lot about perception being difficult. But for now, just bear with me. So this prediction and control problem can, at a high level, be really approached from can be approached either simultaneously or sequentially. So the simultaneous approach is the topic of my my current PhD work, which uses ideas from game theory to actually obtain these highly interactive solutions, which are also optimal in some game equilibrium sense. And so if you're interested, you can follow that link to see some work that I recently submitted to CDC. For the purpose of this work, we're taking a more traditional approach, this more sequential predict then plan approach. However, the highlights of this work are that we're learning a prediction model from data, and that we're also we also use that model to reason about the prediction uncertainty. So the uncertainty in our prediction model comes from the fact that we're using noisy data to be able to regress this model. And so this means that except for a few very simple cases, right, this leads to this unfortunate consequence that the goals of competition and staying safe are somewhat at odds with each other. So to kind of illustrate this, we can consider two rather extreme cases. The first case is where we plan for the ego vehicle in green here, using the nominal prediction for the target vehicle and disregarding any sort of uncertainty in the prediction. And so this can lead to very competitive solutions, but such solutions typically reside at the boundary of your constraint set, which means that if the target vehicle were to deviate from its nominal predicted behavior, this can easily lead to constraint violation. On the other hand, if we plan for the ego vehicle using some set of possible target vehicle trajectories, perhaps using like a forward reachability method, then we can stay safe, but this would become at the cost of a competitiveness. So this really leads to the question of how do we design a prediction model which can lead to competitive but safe behavior for the ego vehicle. So this leads to our approach, our proposed approach, which is in a traditional way comprised of an offline and an online component. So offline, we train this one-step closed-loop Gaussian process model of the target vehicle, which is conditioned on the behavior of the ego vehicle, and this is done using data that's available to us.
Online, we use the last available ego vehicle plan, and then we can roll out a nominal target vehicle trajectory and the associated prediction uncertainties using this Gaussian process model. And then using this information, we can then construct these safety bounds H for collision avoidance, which are then tightened using the prediction uncertainties. And then finally, we can then incorporate these constraints in some sort of MPC problem, perhaps, to solve for the actuation commands for the ego vehicle. So for this work, we specifically model the physics of the vehicles using the dynamic bicycle model. In addition, we also make use of the vehicle's configuration in a Fernet frame, which is defined with respect to a parametric representation of the racetrack. Here we denote using tau. And so using this mapping, then we can define these quantities of vehicle track progress, which is this S as a function of position, the lateral deviation from the center line, EY, and then this heading deviation from the center line tangent, E phi. For the offline training part, then, again, we would like to obtain this one-step closed loop model of the target vehicle. Specifically, our modeling target is this function G here, which outputs the one-step change in the target vehicle state conditioned on the ego vehicle state. So note that implicit in this function is the target vehicle policy pi. And so for this work specifically, we don't have access to real race histories with real cars. So we instead generate data using simulated races on these track segments. So in these simulations, the target vehicle tries to block the ego vehicle from making progress using this term in the cost function, where this QYTV is a weight, which kind of represents how aggressive it's going to try to block. And then using this data, we can then construct the feature and target vectors here using the Fernet frame configurations of the two vehicles, as well as the curvature, this kappa here, this curvature at a number of look-ahead points on the track. And so the reason we do this is so that this prediction model can then generalize somewhat to previously unseen tracks. And we ultimately use a data set of around 5,000 data points to train this GP model. So for the online component then, at each time step, now given the current state of both vehicles in the ego vehicle's future plan, we can generate rollouts of the target vehicle by recursively sampling this distribution that's defined by the Gaussian process model, and then advancing the state. After sampling, we can then compute the sample mean and the sample covariance at each prediction step to obtain the nominal prediction and the prediction uncertainty for each step along the horizon. And then we can generate constraints using these prediction uncertainties. So for collision avoidance purposes, we represent the ego vehicle here as a union of 4 disks in green. And we represent the target vehicle using a body-aligned ellipse with semi-axis lengths A and B. And so that's shown in black right here. So we add to the target vehicle ellipse this gamma standard deviations of lateral and longitudinal positional uncertainty from our prediction model, which is shown here as the blue ellipse with semi-axis lengths AP and BP. And so this then results in this uncertainty expanded safety bound with semi-axis lengths A sigma and B sigma here shown in red. And so it's important to note here that we define this with respect to a slack variable epsilon, which is constrained to be between 0 and 1. And so this allows for this tightened constraint to actually be violated with quadratic cost, but only up to the vehicle extents in black. So one of these ellipsoidal constraints is defined for each of the 4 ego vehicle disks, and then all 4 of these constraints must be satisfied jointly in order for collision avoidance to hold. And so then these are then can be incorporated in a pretty straightforward manner to an MPC problem to solve for the ego vehicle's actuation commands. So okay, now we move on to just some of the simulation and hardware results of our approach. So for both cases, for both simulation and hardware, we set up a vehicle. We set up a scenario similar to before, where the target vehicle starts ahead of the ego vehicle, and the ego vehicle attempts to the target vehicle attempts to block overtaking attempts by the target vehicle by the ego vehicle, again using this cost term that we introduced before. And then we also compare against 2 other predictors which don't explicitly model interactions between the agents. So the first is the well-known progress maximizing model predictive contouring control policy. So this is tuned so that it has the same tuning as the true target vehicle policy, but no blocking term in the cost function. And the second one constructs a prediction assuming a constant linear and angular velocity for the target vehicle. And then for all of our experiments here, we use a horizon length of 10 and a control interval of 0.1 seconds. So these are some simulation videos that I'm showing here. So again, the ego vehicle here is in green, the target vehicle is in blue, and then in red is the the ego vehicle's prediction of the target vehicle. So on the left here, the first set of videos here compare the race performance between the progress maximizing MPCC predictor and the Gaussian process predictors. So here we can see that since the progress maximizing predictor doesn't model the blocking explicitly, the ego vehicle plans as if there is going to be free space to the right of the target vehicle. And so, which leads to this unsafe behavior where it gets forced really close to the edge of the track. On the other hand, the Gaussian process predictor is actually able to predict this blocking behavior since it exists in data, and then avoids being pinned to the edge of the track. So for the comparing now the constant velocity, constant linear and angular velocity predictor to the Gaussian process predictor, we can first see that actually kind of interestingly, both are able to avoid being pinned to the edge of the track. For the constant velocity predictor, this is kind of we kind of got lucky, I guess, because it overestimates the lateral deviation of the target vehicle because of the simplistic assumption about constant velocity. However, for the next term, now we see that again, because of its overestimation, it's actually the ego vehicle is unable to overtake on the inside. Whereas for the Gaussian process model, like the Gaussian process predictor, we're actually able to predict. We're able to again predict the target vehicle's behavior correctly and overtake from the inside while also remaining safe. So we here now show just a quick comparison of okay, yeah, all right. Well, here we're just showing that the Gaussian process predictor is able to maintain a very competitive win rate while also keeping the vehicle safe. So the Gaussian process predictor, the performance is shown in the red line, whereas the other two are shown in the blue and the green lines respectively. And so you can see that the Gaussian process predictor maintains a very low crash rate. And finally, I just wanted to show some of these videos here of our simulation experiments. So admittedly, these aren't driving at very high speed because the floor we have is a very low friction vinyl wood floor, or just a vinyl floor. But on the top, you can see this is the MPCC predictor, which actually shows very similar behavior to the simulation, where again, the ego vehicle gets forced to the edge of the track because of the incorrect predictions. Whereas with the Gaussian process prediction model, it's actually able to stay safe despite a failed overtaking attempt right here. And then later on kind of leverage the predictions to then achieve this overtake on the inside. Yeah, so thank you so much. So I have links to the paper as well as we have made the code open source as well for those who are interested. Yeah, thank you so much.
Thank you very much, Edward. Very interesting talk. And now we are moving on to our next talk. I just open the presentation and we welcome Feng. And before we start, we have seen a lot today, and I promise you, you have not seen this one. Okay. Yep.
Hello everyone, my name is Feng. I'm from Rutgers University. Here I'm presenting you the safe motion control of vehicle spin starting maneuvers. So first of all, what's a spin start maneuver? It's a vehicle driving with two one side wheels. You can see it in the movie, like this one. So dynamically, in this case, the vehicle becomes underactuated and also is unstable. Also, this very similar case is rollover accident. Right. If you cannot keep balance, you will roll over. And to initialize this one, it's similar. Like the rollover, if you run your vehicle on a exit the highway on a ramp, if you can steer very fast, you will kind of roll over. So applications like this show the video, you can pass through some narrow space. Also, you can design some procedures to prevent this rollover sense. So our system is X-axis recent track from the chassis. It can reach up to 45 miles per hour speed. The hardware is ROS, and also we use a onboard Jetson TX2 computer and also a Tinsy TX40 microcontrollers for control purposes. The control input is a steering and also speed control. We have the short brake, small brake to break the differentials problems. The measurement is the speed measurement and also the steering angle encoders. For the protection this vehicle from completely roll over, we add a turning wheels here, as you can see. So the system dynamic is very simple. Actually, it's a bicycle kinematics and pendulum dynamics. We summarized in the following in this lower part here. You can see it's kind of an unaccurate system because the steering input will influence both the planar motion, your XY coordinate. Also, the steering will generate the steering induced torque to help you balance. So it is unactuated. Well, the control strategy here is to, our control goal is to balance this truck, also kind of avoid some obstacles and also some collisions. Meanwhile, we want to prevent any rollovers for the roll motion. So the strategy here we used is external and internal convertible control for this unactuated system. For this balance, for the roll motion control to balance it, we use a balance equilibrium manifold to account for this unactuated properties. CBF function is used for the safety concerns, including the collision avoidance, also the rollover preventions. In the right side, we show this exponential stable EIC controller for this unactuated robot, and also the CBF-based functions, which the previous presenter has discussed about this. Finally, we formulate this problem into MPC problems. So we consider both these CBF functions for planar motion, also the CBF function for the rollover preventions. So safety and balance are considered simultaneously in this problem to achieve this purpose. So in the right side, we show our algorithms. First, we show a 3-line track. Since we test our track at a different speeds from the low speed to high speed. So the lowest one I achieved in my experiment is about 0.8 meters. For this one, as you can see, the trajectory error is about 0.5 meters. So it's quite large compared to the high speed ones. When you reach your speed at 1.6 meters, you can reduce the errors. Because you increase your speed, your steering induced torque is large, so that you can balance your system at very precisely. Since roll motion and planar motion is coupled, so when the roll motion error is small, the planar motion are also small. Okay. Next one, I show a short video here. You see, this one is an experiment. Oh, sorry, it's not able to play it. So we tested at the video shows 0.8 meters skin star movers. Next, we try this circle track. As you can see, when the speed is too low, you cannot do this maneuver. Why? Think about you ride bicycles trying to make a sharp turn, turn. You need to provide some torque to balance yourself always in that circle, right? Because this steering induced torque is related with your velocity. Where velocity is larger, your torque is larger, so that you can balance it. Okay, also we can see that with the speed increase, your torque is larger so that you can achieve the better performance with smaller errors. Next, we try this obstacle avoidance of this experiment. We tried 2 different speeds, as you can see here. We have an obstacle at 50 here, and the radius is about 1 meter. The target position is at 10. So as you can see here, with the speed increase, actually your motion, your trajectory becomes more safer, which means it's kind of more conservative, right? Because your speed is low, you can do some risky motions. But your speed is fast, you are always trying to keep safe, so that you make some conservative decisions. Next, we show the result how to initialize this one. So I think this video. This you cannot show it. So as you can see from this figure here shows the rotation angles of your roll motion. At very beginning is 0. So then at 4 seconds, you make a sharp turn here. Your steering angle suddenly increases to about 30 degrees, so that in this case, your truck body roll angle increased to 40 to almost 50 degrees. So that in our case, we can actually automatically achieve this skin start maneuver initialization without use any ramp sense to help it. So, but the case is that in this case, since your speed is fast, you're easily to roll over. I tested in my experiment, It's very easy to roll over things if without that training wheel to protect it. Also, we're trying to predict these roll angles. Because we have this it's a balanced equilibrium manifold here, which is related with the steering angle input. See, this is a steering angle change here in the left side. The right side, the blue curve is measured from the MU. The yellow curve, sorry, the brown curve is what I obtained from this equilibrium manifold. In this case, you can see the prediction actually very similar to these actual values. In other words, if I want, I can purposely design this steering input to tilt this vehicle body to achieve some roll angles. So the conclusion that we do this skin start maneuver automatically with the build dynamics model, also which demonstrated it is possible to guarantee this balance and tracking, also maintain this safety here. So our future work is trying to achieve this autonomous initialization in a better way. Also use some learning-based method to improve the roll motion dynamics, especially. Okay. Thank you.
Yeah, thank you very much. Okay, yeah, we have now our last talk, but 1 second before, because I think, again, this topic is too cool. So I make myself a host right now and share my screen because the videos work on my computer somehow. And I want you to see the videos. So maybe you can comment it.
So just two-wheel drive is a very low speed. As I told you before, the speed is low, it is challenging, right? Because the torque is small. So it's like this. The right side is the one in the films. Same. Maybe next one. This one is about how to initialize it. You can see around about 3 meters per second. First, then I suddenly make a sharp turn, it can initialize. If without a training wheel, we are over.
All right. Thank you very much. And now we have our last talk. Hi, Elizabeth. I just open your presentation and then the stage is yours. Okay. All right. Thank you for being here.
Hello, my name is Elizabeth Keefer, and I'm from Auburn University's GPS and Vehicle Dynamics Lab. As we've talked a lot today, recently there's been a wave of autonomous vehicle challenges, such as RoboRace and the Indy Autonomous Challenge, the IAC, that's arisen to push forward innovation in research in autonomous vehicles. I was fortunate enough to be a member of the Auburn Tiger Racing. Through our lab. We competed in both competitions, the one last October at the Indianapolis Motor Speedway and the one this past January at the Las Vegas Motor Speedway. I, along with my team lead, Will Bryan, helped develop the motion planner for our team. We knew that the motion planner would need to be safe, efficient, stable, and predictable. However, because of the structured and semi-predictable environment of the competition, we were able to favor efficiency over complexity. So today I'll be presenting to you our solution to the path planning problem from the 2022 IAC at CES competition. We surveyed a wide range of planning algorithms such as model predictive controls and artificial intelligence. While these are like state-of-the-art and really good algorithms for unstructured environments and kind of unpredictable scenarios, we found that these were typically very computationally intensive or overly complex for this particular application. We also looked at sampling-based approaches such as probabilistic roadmaps and rapidly exploring random trees and many of their derivatives. These, some of the pros for this is you don't have to discretize the configuration space, which in our case would be our track. And they're good for higher dimension spaces. However, none of these pros really shine through for our application. So we settled on a graph-based approach, which because we know the track bounds ahead of time, we're able to fully discretize our space, and because of the predictable nature of the ego vehicle and the defending vehicle, we were able to simplify our environment in a way that fit well with a graph-based approach. So our first step in our planner was the graph generation. We can make several assumptions as the vehicle would stay in the track bounds that are known and validated ahead of time, and that the ego vehicle will always be moving in the forward direction. Meaning our graph would be directionally cyclic, which would simplify our edge configurations, which you can see here. Our edges are computed at runtime, but could easily be pre-computed beforehand. And then for our planning algorithm, we went with A* as opposed to some of its more complex derivatives, because it's simple, efficient, and an optimal graph search algorithm that's often seen as an extension of Dijkstra's algorithm. However, it takes an element of a best first search method by having a goal-oriented guiding heuristic. This heuristic in more basic applications is usually either a Euclidean or Manhattan distance between a goal and a vertex. However, for our implementation, we used 4 different costs. The first being an object cost, which is a penalty for a vertex being close in the proximity of an object's predicted trajectory. So farther away from the predicted trajectory, the less it would cost for that vertex. We had a dynamic cost to keep the path dynamically feasible. For our implementation, our dynamic cost was a function of the lateral acceleration. We also had a distance cost from the ideal race line, which is a penalty due to the deviation for a vertex's deviation from the race line. So in instances where there aren't any objects present, it keeps the path close on the ideal race line. And finally, we used a more classic heuristic cost for the Euclidean distance from the goal to the vertex. And then finally, the outputted path of the A* is often has discontinuous curvature, so we just applied a moving mean for smoothness and dynamic feasibility, and it also helped the motion controller track the trajectory. For our experimental setup, we used LGSVL Simulator, which is an open source high fidelity simulator. We chose this because of its ease of use and its real-time testing environment. And we were able to integrate our full AV stack for software in the loop testing. It conveniently had the full Las Vegas Motor Speedway track. We also had an object simulation, which we were able to simulate static objects and dynamic objects. For static object testing, we randomly placed objects in our vehicle's path, or we explicitly set them in configurations to test more like edge cases. For dynamic objects, we set the objects in a trajectory similar to the path of the defending vehicle at the Las Vegas competition. We tested a range of speed differentials between the dynamic object and our ego vehicle. And for our testing, we made several exceptions, such as neglecting perception and localization uncertainties because it was outside the scope of this paper. And we had it set 100-meter max perception distance, meaning that if the vehicle was within 100 meters of an object, it could see it or detect it. So here's kind of one of the results. We consistently saw results, paths like this. The path you see in orange is the path outputted by the planner, the race line being blue and our ego vehicle being the blue dot. So the green square represents a detected object. If it was red, it means it would have been like outside of that perception distance. So we're able to see paths like this and consistently avoid objects at speeds ranging from 35 meters per second to 75 meters per second. And in this instance, where we explicitly set objects, the ego vehicle sees the first 2 and plans a path. However, if it continued forward on the orange path here, it would run into the other 2. However, when it detects the third object, it plans a path and successfully navigates around. And then finally, here's an example of a dynamic test. And here the ego vehicle detects the dynamic object, starts doing the overtaking maneuver, and successfully closes back into the race line. One of our goals was also to have a planner that would iterate very quickly. And so we saw that we had average calculation times between 0.7 and 0.9 milliseconds, which runs as fast as our localization stack. And then when we took this to real world testing on our Dallara AV21, we found even faster calculation times of 0.32 milliseconds. There's a couple of reasons why we think that it's faster in the real world, because one, the simulation computer is having to run the simulation environment and our autonomous vehicle stack. And secondly, the computer on the car is much faster than any simulation computer that we have. This extra time allows for future added complexity to our planner, allows room for future added complexity to this planner as the scope of the competition widens. So for our future work, we want to expand the local planner to work not only on ovals and triovals, but also on road courses. We want tighter integration of opponent prediction and motion planning. And we want to use a vehicle model for dynamic costs instead of weighting lateral velocity to ensure feasible trajectories. So, thank you.
Thank you very much.